Alright, the next two practice problems are just dealing with weak acids and bases again. Actually, these both be dealing with finding the pH of weak bases. So it's the same general process, only difference is we're dealing with a base now, so it's going to be a little bit of one more step to get to the pH as opposed to just the negative log of the concentration. So what I would recommend now is you can see the practice problem right there. Find the pH of 3.5 molar solution of ammonia, and we see the equation right here. Go ahead, pause the video, give this one a shot if you think you can handle it, and then I'll go ahead and solve it too so you can resume it when you're ready to look at it. Same thing with the next question. If you're feeling comfortable with it, go ahead, pause it, give it a try, and then take a look at the video afterwards. Alright, welcome back. Let's take a look at this problem then. So with this one, let's set up an ice table. Always set up an ice table. ICE. And we need to find the pH of this solution right here. So we see ammonia ionizes. It turns into ammonium and hydroxide. And we have water there, which is a liquid. So in our ice table, we're going to ignore that one. I'm going to put a cross through it. Doesn't mean that it doesn't matter. It just means in our equilibrium, it's not going to be factored in because it's a pure liquid. Okay, and as always, our concentration is given to us to begin with, 3.5, and then those ammonium and hydroxide both start at 0. Ammonia is going to decrease by X, ammonium increase. So at equilibrium, 3.5 minus X, and then plus X. Those are our equilibrium concentration values. So let's take a look at the approximation rule right here with this 3.5 minus X to see if we need to consider in that minus X. So once again, we just take this KB or KA, whatever our equilibrium value is, and then plug it in for X just to test it out. So 3.5 minus 1.8 times 10 to the negative fifth gives us 3.49982, which is pretty much 3.5. So really, this minus X right there isn't important. We can leave that out. So we can say the equilibrium value of NH3 is still going to be 3.5 molar. This is a weak base, so it's not going to ionize by very much at all. So let's take those values then to a new screen. So Kb for this particular reaction right here is going to be equal to the concentration of NH4 plus times the concentration of OH minus, those are our products, divided by the concentration of NH3 in our solution. So we've already said that the NH4 will be X, the OH minus will be X, and the NH3 is going to stay at 0.3 because we get rid of that minus X that's on it. I think I said 0.3 before, and I'm at 3.5 is our concentration of NH3 since the X didn't change it. And we know that Kb for this particular reaction in the end is equal to 1.8 times 10 to the negative fifth. And then we can rearrange this and we can solve for X. And X is going to equal 7.9 times 10 to the negative third. And that would be our molarity. So X is 7.9 times 10 to the negative third. And since the X value, we've already seen up here, the X is going to be the concentration of the NH4 and the concentration of the hydroxide. So that means that this value right here would be equal to our concentration of hydroxide, the OH minus. So now we can take the negative log and get the POH. So the POH would be the negative log of 7.9 times 10 to the negative third. And that has two significant figures, so we would record this as 2.10. And pH would be equal to 14 minus the POH, which is 2.10. So our pH for this solution then would be 11.90, and this would then be a basic solution. Alright, that's that. The only difference really between this one is when we calculate out our concentrations at the end, we're getting the concentration of the OH minus, and the OH minus then will give us the POH, and we use the POH to get the pH. So it just adds that extra step right there to go from POH to pH. So we'll take a look at another practice problem. This other practice problem is kind of general same thing. So I don't think this particular problem is on your PowerPoint that I posted online. If not, just write it down somewhere. It's pretty quick, but we have a 0.15 molar ammonia solution, and it has a pH of 8.75, and we're going to find in this case the equilibrium constant for this base. So the equilibrium constant that we looked at for the last question, it was this exact same equation, or exact same formula, which is 1.8 times 10 to the negative fifth was its Kb. But remember, it's temperature dependent, so we can't assume that just because last time we looked at ammonia it was 1.8 times 10 to the negative fifth, that it's going to be the same thing this time. We got to assume that it's going to be a different temperature, so it's going to be a slightly different number. So we have the pH, which tells us the H plus concentration, but in this reaction right here, it deals with the OH minus concentration, which means that we're going to have to convert this pH over into the POH so that we can find the OH concentration. And so let's remember that POH would equal 14 minus the pH, and our pH is 8.75, which means that the POH for this particular guy is going to be 5.25. And we can take 10 raised to the power of negative 5.25, and that will give us the OH minus concentration, which we can then find to be 5.6 times 10 to the negative sixth. Alright, let's remember that number because we're going to use it in a couple different places here in the next part. Let's clear the screen and take a look at an ICE table. So ICE. Remember, H2O, that's a pure liquid, so we're not going to factor it in. This guy starts at 0.15 molar, 0 and 0. This is going to change by minus x. This is going to increase by x. And then at equilibrium, 0.15 minus x, and then plus x, plus x. But wait a minute, we know what the OH minus concentration is at equilibrium because we just calculated it from the pH. So that OH minus concentration we found was going to be 5.6 times 10 to the negative sixth molar. And here's the thing, so if x in this case equals 5.6 times 10 to the negative sixth, that means ammonium's x is going to be equal to the exact same thing. So this value right here is going to apply to both ammonium and the hydroxide. They're a 1-to-1 ratio, so whatever the hydroxide equals, its counterpart, the cation, has to equal the same thing. And this x right here, over on equilibrium for ammonia, it's also going to be 5.6 times 10 to the negative sixth. So we can take all three of those and plug them in to solve this for the Kb of this particular reaction. Let's go to a clean screen to do that. So remember these numbers, 0.15 minus x, plus x, plus x, and all those x's are 5.6 times 10 to the negative sixth. So Kb is going to be equal to the concentration of ammonium times the concentration of hydroxide divided by the undissociated ammonia, NH3. And we've already said that the value of the ammonium and the ammonia is 5.6 times 10 to the negative sixth. And we can square that value, because since they're both the same thing. And we're going to divide that just by 0.15. If you take a look at that minus x, it's not going to make any difference, because 5.6 times 10 to the negative 6 minus or this minus that right there isn't going to be equal to anything different than 0.15. And so then we can just plug all that in, solve for this, and get 2.10. Nope, get rid of that 0. 2.1 times 10 to the negative 10th. And that's it. So notice that this value is different from our last KB that we looked at in the previous problem, where it was 1.8. 1.8 times 10 to the negative 5th. It's different just because of different concentrations, because of the temperature difference, anything like that.